And we are now recording. Let's get the slideshow set up from the current slide. Now, can't quite remember if we did this slide or not. I don't know if this was where we ended or where we were going to begin this time. It seems like I had this on already, but I don't recall. Do you?
That's what we were left on.
This is where we're going to start. Okay. All right. That's what my mark was, but it seemed like to me I think I talked about something like this before, but we may not have shown this. Yeah, I don't. Now that I look at that, the second part there. All right, this is example 6 on page 582. Were there any questions before we get started? No? If there are, I'll be glad to try to hit them.
There was some homework that it was just a little confusing, but I forgot which ones it was.
But what?
I forgot which ones.
Oh, okay. If you have them, we can hit on them. Because the odds are, if you're confused about them, the real good chance someone else was too.
I think it was number 3 on page 587.
587, the previous section. Wait, no. It's in this section. I was looking at the wrong page. Okay. Number 3, you said. I'm sorry. Okay. All right. Example 3 was back in the text, it wasn't problem 3, it was example 3. And that was back on page, the bottom half of page 580. Okay, what I think I'll do here is let's see if all right, this has a lot of white space on it, so I'm going to use it. A rocket model follows the trajectory. Let me get my pen activated here. Okay. Model rocket follows the trajectory. C of t is equal to, now, 80t, 200t minus 4.9t squared. 200t minus 4.9t squared. Okay.
So on that one, would you do x is equal to 80t and then on third t?
That's it, exactly. Yeah. Hey, and here's the symbol. Okay. Oh. And here's Marcus.
If you plot it out, would it be a graph?
Okay. Say again what you said.
So once you said that you put x and then solve for t, then you replace t on the line with x.
Right.
And that would, if you plot it, that would give you a parabola.
Yeah. And whether you plot it or not, that will be a parabola form. Yeah, that's what I go back and read the problem. Show that the path traced by the bullet. Here it's a model rocket, not a bullet, so I guess it does matter a little bit. Yeah, I don't know why one place says, yeah. Is a parabola by eliminating the parameter. Yeah, you'll see you have a quadratic form, and that's a parabola. I think that's all there is. Does that answer? Okay, yeah. Any others? Ask if there are any questions first. So if you got questions, that's what we're dealing with now. 5 on the same page? Okay, I still have it marked. Graph the parametric curves. Include arrows indicating the directions of the motion. Okay. Let me erase this ink. Okay. The first of these is TT. Okay. And this is from minus infinity to positive infinity. Okay. Now, let's draw the graph. Might need more than that, but we'll see if we can get by with it. Okay, give me a T. Second? 1? Okay. And then what would be your coordinates here? This is the XY plane. 1, 1. So that'll be right here. Give me another one. 0. What would that be? 0, 0. Another one. Yeah, it'll be the y is equal to x. You can see that from that right there. Okay. Yeah. Say that again.
What it's asking there is just to choose a T and start applying.
Yeah, but the other thing I needed to do, and I sort of botched up here a little bit, is I drew it as a straight line. What I need to do is an indefinite line, but then have the arrow indicating it's moving in that direction. See, this is a curve, not just a line y is equal to x. This is a pathway, which means it not only plots out a pattern, but also has a direction. Because as your t's are negative, you're way down here, and as they're getting more positive, they're out there. So this is the direction of increasing t. That's the only thing you do beyond that. Okay? And what was was there another question you had with that? Okay. Need to see some of the others? It is an interesting problem. Let's look at some of the others. The B one is sine t sine t. Okay, so here I'm going to do the different color. You want to pick one? Huh? Okay, I'm going to do, that was a dark blue, here's a lighter blue, and this is going to be sine t sine t. And also the same limits on t. No. 0 to 2 pi, sorry. Yeah, okay. Give me a t. Second? Pi halves, okay. And what would your sine t be then? Your x? And y would be 1 too then, right? So you would be right here. Okay? Am I correct? Why didn't you start at the beginning? Like 0. Okay. Where would that go? 0, 0. Okay. Now pi halves is fine. How about pi? Second? 0, 0. Okay. So what are you doing here? Is that what you've done? From 0 to pi halves, you go up to here. Oh, wait. Got that wrong. Okay, then from 0 to pi, you come back, and from pi to 3 halves, pi to 3 halves pi, you come back down here to minus 1, and then you go back up here again. So you start here, go here, go here, and then go back here. So it's just a line segment between -1, -1, and +1, +1. And it actually goes up, back, and up again. Right? You see what I'm saying? Okay. Faith is here. Perfect attendance again today. Way to go, team. Okay. By the way, another way to go here. A quarter of you have turned in a paper already. Way to go. 3/4 haven't. That's not quite as good, but still. Okay. Let's get them in. Okay. What we're doing, yes.
What chapter is this?
This is chapter 11. We're reviewing some homework exercise. This is number 5. I didn't put that down, did I? This is page 587. Let me go back to the dark color. This is, well, it didn't take, did it? Page 587. This is 1.1 exercise, 11.1 exercise, and this is number 5. Okay, we had done the A part up here, and then we were just doing the B part down here. Let's go to the C part. What color you want C to be? Second, red. Okay, I'll go with the lighter color red. There we go. So here's C. E to the T, E to the T. And this is from -infinity. Okay. -infinity less than T less than positive infinity. Okay? Now, give me a T. 0. Okay? And what would the values be then? E to the 0. Anything, second? 1. Anything to the 0th power is 1. So we start at 1, 1. And where do we go from there? You tell me. Give me another T. 1. And what would that be then? E, which is about 2.7. 2.7. So that would be somewhere maybe up here. So I know between 0 and 1 we've gone in that direction. Give me another T. 2. And that would go up to fairly close to 9, not quite 9, but it just keeps on trucking. So it looks like to me it just keeps on going in that direction. But we didn't start with negative infinity, so give me something less than -1. And what would that be? So yeah, 1 over E, which is, right? But, say it again.
0.37.
Okay, just a little bit less, yeah, less than 1/3. So it would be down here. Give me another one. -2? Is that what you said? What would that give you? Something a little bit less than 1/9, or greater than 1/9 or something. So basically, it doesn't start at 0, never gets there, but it goes in this direction, always positive. So you don't have anything negative on this one. It doesn't start at 0, but somewhere close. Because if you picture the E curve, that's what it is, right? Okay. So down here, even if -1 million, or something like that, E to the -1 million is almost 0, but not quite, And that's where you'd be starting and just taking that part of the line. Okay? Now, the D part. Give me a color. Green, okay. And we'll do the D in green. And that was T cubed, T cubed. Okay. And that goes from, oh, -1 to 1. Interesting. Okay. Give me a t. 0, okay. What would that give you? 0, 0, okay. Another t. 1, what would that give you? 1, 1, that gets up to here. Another t. -1. It gives you -1. Okay. Unfortunately, we do need something in between. Second, 1/2. What would that give you? Second, if t was 1/2, 1/8, 1/8. So it would be somewhere here. So I'm pretty sure it's doing like this. Okay, starting at -1, -1, and just going up to +1, +1. That's all, folks. Just stops right there. Because you did here. If you had been negative infinity to positive infinity, it would be the whole line just like the dark blue line was. I guess that's instructive. It's interesting anyway. Okay, the presentation. Okay. Is that not what you're remembering they gave us in the back? Huh? Okay. Let's just see. This is 11-1, wasn't it? 11-1 exercises 5. Yeah, from -infinity to infinity going in the upper direction. Minus the B one is what was the light blue in there, and that went from 0 up to pi halves, then down to, that's at 1, 1, then down to -1, -1, then back up to 0 again. So that, I think we got that right. And then C just went from open circle at 0 to positive infinity. And then the D just went from -1 to -1, 1 to +1, +1. Okay. They got it right too. Good for them. Okay. Any others? Does that answer your questions on those? Okay. Any others? All right. Let's go back to where we left off before, and that was on this figure. So it was example 6, page 582. I don't think we had started it, had we? No. Okay. So let's do that. C of t, very similar to what we were just doing, or this is C1 of t. I'm going to go back to a dark color again. Okay. C1 of t is this function here. T cubed T6. Okay. Describe the motion of a particle moving along each of the following paths. It's basically the same thing we were just doing, only it's not a linear path anymore, or it's a portion of a linear path. This is something else, but let's determine what. Now they don't put any restrictions on the t's, so we're going to assume that the t's are all real numbers. Okay. So, you tell me where to begin. I'll ask you how to begin. Give me a t. Any suggestion on t? 0. Okay, I like it. And what would that be? 0, 0. Okay, that would be starting right here. Okay. Give me another t. 1. And that would give you 1, 1, which I assume will be right about here. Okay. Give me another t. Actually, all real numbers. Yeah. Second? 2. Okay, what would that give you? First one would be 8. 60, no, not 64. Wait, is it? Yeah, yeah, t cubed would be 8. Yeah, and that would be 64. You're absolutely right. So 264, I don't think I can draw that on the scale we have here. But you see, it is heading up that parabola in that direction. Okay, so we'll buy that so far. How about a negative? Okay, -1 would be what? Now 6. Even power of a negative number is always positive. -1, 1. And that would sure enough be right here. So I'm willing to buy that it is going in this direction, that direction, and on up like this. Would you buy that? So -1 cubed is -1. -1 to the 6th power is -1. Okay, square -1. +1. Same thing you did before. You found the easier way to do it, but that was sure enough true. Okay? Okay, anytime you raise a negative number to a positive power, it's going to be, even power is going to be positive. Negative number to an odd power is always going to be negative.
How do you determine the direction?
Okay, you take from small t's to large t's. So any minus t there, any minus t, and the more negative you have it, the more negative the x is, and the more positive the y is. And then as they get less negative, they're coming down the curve. At 0 is 0, 1 is 1, 2 is to be 0.864. So it's way up there somewhere. So the arrow is in the direction of increasing t. Plot several. Make sure they're not backing up on each other or something. That's what we had to do a few on that last one. Okay, so that's the direction. That's the A part. The C part is C2 is t squared t to the 4th. C2 is t squared t to the 4th. And we're going to assume all real numbers. So give me a t. 0, 0. Okay, I found that one. Next. 1, 1. I got that one. Okay, it seems to be going in the direction of the light blue arrow so far. Give me another one. Negative what? I'm sorry, I couldn't hear.
I said
-1. -1. So if t was -1, what's your point? I can't hear. It's going to be 1, 1 again. Okay. So give me another negative number. -2 would be 416. So the minus numbers, as they get, the minus numbers are coming downhill and the positive numbers are going uphill. And at 0, 0, they stop. Okay? And that's at the origin and go up. So the minus numbers, the larger the negative number is there, way up there. Large for x, but even larger for y. But up there. And then as you get less negative, they're coming back down. You get this one and this one. But then as you go positive, then they go back up and follow that same route. So that's why they have the green arrow coming down for t less than 0 and the blue arrow going up for t greater than 0. But tracing the same path there, but never comes over here because neither one of those, especially the x value, will never be negative because it's squared. Okay? Now, The next one, C3, is cosine t, cosine squared t. Well, here it is down here. I didn't see it was writing. Okay, here's C3, cosine t, cosine squared t, and I just drew over. Ah! It's not what I meant to do. Well, I'm okay. Okay, there's C3. I guess I could have included the title of it. In fact, let me do that. Well, that time I could have done it, but never mind. Okay. Here's your C3. All right. Give me a T. So 0? What would be your point then? What's your point? 1, 1. Very good. So t equals 0 starts right there at 1, 1. Okay? Then give me another one. I don't like it. Half pi. Okay. By the way, they don't have any. Okay. At pi halves, where are we, Waldo? 0, 0. Okay. So from 0 to half pi, we've come down the green arrow here. So this is t equals 0 to t equal pi halves. Give me another one. Pi. And what would that be then? Negative 1, 1. So you're up here. So this is t equal pi right there. Then give me another one. Second. 3 pi over 2. And then you would be 0, 0. So what we've done so far is gone down the green curve and back up, but then once we got up at the 1, 1, we're going back down the blue curve. And then from then on, you go back up the blue curve again to 1, 1 again, then come back down. And you're stuck in an endless loop there, going back and forth along that parabola. Right? Never get outside there because cosine never gets outside plus or minus 1. And cosine squared will never get outside 0 to 1. So there you go. Back and forth, back and forth. Okay. And your t is infinite, but you just keep repeating the path over and over and over. In fact, if you started at negative, wherever you started along the curve, you do that over and over because your t's are good forever. All right, make sense? All right. That was example 6. Now, see if we can do example 7. I think this is part of it. I think I'm probably going to have to lose this really soon, though. Okay. Sketch the, excuse me. Oh, man. This happens. Well, again today, as I was telling Emmanuel, I almost finished lunch, but didn't quite. Of course, what I still had to do was drink my water, and I got a sip or two, and that's all. So now, all of a sudden, I'm drying out. Eyes are dry, my throat's dry, everything's dry. See if we can make it. Example 7. Sketch the parametric curve C of t. Oops, I can't do it here. C of t is equal to t squared plus 1, comma, t cubed minus 4t. All right. Now, I wrote my t cubed right on top of my comma, so I lost it. Okay. It looks like that's what I did. Have I written it right? I believe so. All right. Give me a hint of what you would do first. Second? T equals 0? Is that what you said? Okay, I don't know what you said. What did you say?
I said value, some value.
Yeah, enter some values for t. So let's start with t equals 0. T equals 0, what's your x value?
1,
And what's your y value?
0.
0. 1, 0. Then where to begin there? It says sketch the parametric curve. So I think I will come over here and sketch a parametric curve here. So 1, 2, 3, 4. 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5. Okay. So at t equals 0, I was at 1, 0. 1, 0, right there. This is t equals 0. Okay, give me another t. 1. Okay, when t is 1, what do we have? A little louder. 2. Y is what? Minus 3. Okay, so 2 minus 3, somewhere down here. Okay, that's t equal 1. Okay, give me another t. 2. T is 2. T for 2 and 2 for t. What would that be? 5 and 0. Okay. Whoa, that's not right. I'm already off scale, am I not? Good. Didn't do planning very well here. Okay. Let me, sorry to do this, but I was trying to think if there's any way to salvage this. I don't see any. So, let's set up my scale here. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 6, 5, 1, 2, 3, 4, 7. Okay. Okay. Yeah. Right. Yeah. This is perfectly fine, but if you ever prefer, there's one on that wall too under that chair. So whichever you want to. I've got another one up here. So there's 3 in the room, 1 here they just put in, and these 2. Not many plugs for a big room like this. So anyway, we had 1, 0. Then the next one was 2, negative 3, wasn't it? And the next one was 5, 5, 0. Okay. All right. Give me another t. What again? 3. Okay. Yeah, this is t equals 0, t equal 1, t equal 2. What happens when t is equal to 3? 10 and 19? 15? Okay. 10 and 15. So I don't think I can get it there. So 10 and 15. It's going on up here somewhere, like really fast. Okay? Let's get something less than 0. Maybe a negative 1? What would that be then? 2? And what? 3. 2, 3. 2, 3. All right. There we have it. And I bet you negative 2, that's t equal negative 1. T is equal to negative 2. I bet you it's going to be 5 again, isn't it? Is it? 5, and then what you get? 0. Okay, so it comes back here. So basically we have a curve that does something like this and goes to infinity that way, and does something like this and goes to infinity that way. Almost looks like a ribbon or something like that. Okay, there's the curve. Now, what can we say about that? Well, number one, your x value is always positive. Always positive. No matter what t you put in there, that's going to be positive. Never less than 1, which you reach when you get t equals 0, but then beyond that is positive. So it's, in a sense, the x's are x's relationship to t is that if t goes positive or negative, x stays positive. So it's even, x is an even function, okay? And it always stays positive. Whereas y is an odd function, and since y, as it increases or decreases, but wherever it's going, is saying opposite. So the y's are repeating themselves above and below, and sure enough they are. So that's your graph of it, okay? Now, why didn't they graph this one? Okay. What would happen, I did, this is 2 and -2 down here, and 3 and -3 were way off scale. They did 2.5, which they could get on the scale they've got here. That was 5.6, so t is equal to 2.5, 5.6, no, 7.25 for for the x value. That's 2, 3, 4, 5, 6, 7.25 for x, and then 5.6, 1, 2, 3, 4, 5. It would be up here. Yeah, my graph isn't too far off, and minus would be down here, maybe a little bit off there. But sure enough, that's what you got. Kind of a Dory the fish or something like that shape there. Why they didn't show a picture of this one, I don't know. Okay. All right. What else are we supposed to do? Oh, they did graph it. See, I was just looking at the first two and didn't look at it. Here's what they did, and this is pretty, I don't know if it's all that instructive, but it certainly is somewhat interesting. I guess that's as good as I can do. Okay. So here's the curve. What they first did, they first graphed the y-coordinate. And the y-coordinate was a cubic function, odd function, reflected across the origin. And sure enough, it is reflecting exactly that. The x, why they graphed x first and then y second, or y first and x second, I don't know, but they did. And that just gives you this curve here. It is a quadratic. It would be a parabola, okay, the vertex being down at I would say one's where the value is there at t equal 1. But it is a parabola. Why they didn't show the rest of it, I don't know. They didn't say, well, they didn't need to. T is equal to 0, 1, 2, 3, 4, 5. On like that, you don't see 5 on here or even 3 on here, of course. But you could have had a negative 1 in there, and it would have completed the parabola almost this way. All right. Okay. I think that's all we need to say about it. And then it's kind of like you're putting them together. I mean, it sure looks like this half is that there. Yeah, okay. But when t is equal to 0 over here, you're right here. So your y value is 0, but so is your, oh, that's not t. T equals 0, you're on the x-axis, but you're not at value t equals 0, you're at value t equal 1, okay? And the y values, well, everything's on xy plane here. No. Here's what's wrong. Okay, I knew something was fishy here, and here's what it is. This is the xt graph. This is not the xt graph. This is the xy graph, and that's why it was just so confusing. I thought this was xy. It's not this. I mean xt. This is xy. So that's what I was looking at. That's why this is exactly that, because these are both xy graphs. Duh. Okay. If you had drawn an xt graph, you would have had a parabola whose vertex is at positive 1, and it's going up like that. And I was thinking, how in the world did they get that? It isn't. That's a xy graph. The positive half of it, the latter part over there is the negative half. Now, what I didn't do when I was drawing mine is I didn't put my arrows in here. Okay? The arrows are coming like this, like that, like that, like this, and like that. And that's what they do show here that I had failed to show. Okay? Let's go back and improve and or expand this a little bit. Okay. And sure enough, that's your arrows. They only showed the positive part of this one, and that's what was confusing me so badly. I thought that was a xt graph, and now that I look at it, it's nowhere close, so it couldn't have been. So, I don't know. I mean, that's what it is. I don't know if you you find that particularly instructive or not, but there's what it is. Now, the next thing they're going to talk about is a cycloid. Have y'all hit cycloids before at all? They're really interesting phenomena. Okay? And here's what a cycloid is. It's basically, you take say a wheel. Okay? You're going to roll this wheel in the positive x direction. The center of the wheel you're going to have sitting here at 1. It's a wheel or circle of radius 1. And here's your first point of contact right here. So you're going to follow this point on the wheel as it turns. Now, as this wheel turns, certainly the blue dot gets lifted here, but it also gets moved that direction. So sure enough, it's going up here, and right here is this position. Right here would be, if this is 1, this would be 2 up here. And at some position right here, the blue circle would be exactly up with the blue dot on top. So the blue dot is going like this, and then it comes back down until this is 1 revolution of the wheel to go from 0 to 2 pi. Okay? Halfway in between at pi, the blue dot was at the maximum position here, which was 2. Because it's a radius of 1, it would have been at the top 2r above pi. And then once it touches down at 2 pi, then it picks up and goes again and again and again. Now, that's the cycloid, okay? The figure of a cycloid. As time is increasing, it's going like this, like this, like this. So it's pointing always in positive x. If you had allowed it to start back here, it would have still been doing that, positive x, only now your t's would have had to be negative. If the t really stood for time, we don't have negative time, so that's why we started here. But if t was just any old variable, it could have been there. So there's a cycloid. Kind of big deal. I mean, not too impressed with it yet, until you realize how much they occur in nature. And actually, the one I'm going to describe to you is going to be, it's not an anticycloid, but it's sort of one upside down. If you had flipped this over, then it would have hung like this, and like this, and like this. Does that remind you of anything? Power poles and the power line in between, or telephone line, whatever line you want there. Most people call them telephone poles, but most of the time they're power poles. The telephone company may use them or may not, but most of the time they are power poles, the ones you see. And sure enough, that loop on the bottom like that is exactly how the line falls. Okay? Will you ever get that line perfectly taut? No, you can't. There's always going to be some curvature in it. Okay? Unless, of course, you get it as tight as you possibly could when you're running that line, say in the middle of summer, okay, hottest time of the year, and you get it as tight as you can, and then you wait till the weather cools. What you do then is pop power poles, because they cannot, if you had it as tight as you can, which has a little bit of a loop in it, but then that's in the warmest weather, when that line contracts, it will actually break poles. Believe it or not, it will. It has. Same thing about, well, it's not quite the same thing, but very similar to other situations you find. That coefficient of linear expansion that you have in physics is a pretty powerful tool. It may seem pretty small, but it's a pretty powerful tool. So this is a cycloid. Here are the equations for that cycloid, okay? And this is for the upright one like we just saw. it's hard to see. X is equal to t minus sine t. Maybe not really clear what that is. For y is equal to 1 minus cosine t. Okay? Both of these, if t could be negative, would allow for negative values. But if t is indeed, depending on time, most of the time that will be always counted positive. But the x is always increasing. As t is increasing, so is the x. As y is increasing, as t is increasing, y starts out on the downhill because t equals 0. 1 minus cosine of 0 is 1. That would be 0. It would be starting at 0. And then the y increases to the midpoint, okay, and then decreases, increases, decreases. So it's moving back and forth. X is increasing only. Okay. Now,
Why is that equation in terms of
say that again.
Why is it in terms of t?
Why is it what?
In terms of t.
Oh, that's just a parameter. I mean, you could have done S or something else, but a lot of times it will be representing time. I mean, you could choose any variable theoretically that it could do, but in reality, it's going to be kind of a time dependence. You know, if something's moving along that, the wheel is turning and that point on the wheel is moving along that way. Now, the interesting thing is, in this picture, in the old edition, that was how it looked. In the new edition, they actually show it at pi. They show the first two pretty much like that, but then the third one, they actually show at pi. And I think that gives you a lot better picture of what's going on. Actually, if they'd have done both of them in there, that would have been even better. Okay, so that's our equation 6. And I wondered if it would make sense to let's just kind of picture what's going on here. The sine t is an increasing function up to a point, 0 to pi, and then it's decreasing from pi to 0 to pi half. It's increasing, decreasing 0 to pi half to pi, and then goes negative and that kind of stuff. But the ruler of the roost here is the t. As t increases, this constantly is increasing. Sine t is just cycling back and forth going plus or minus 1. So sometimes it's going in fits like here, then it's slowing down, and then it fits, but it's never backing up. You know, it's always moving forward. This, on the other hand, is going up and down. It started at 0, goes up, and when this is 0, it's the max. Now, it started at 0, because when t is 0, that's 0. Then it went up to the max when it was at pi, which is minus a minus 1, and then the y just goes up and down in a fairly regular pattern like that. Okay. And we saw that on the graph. But let's go back to the graph. You see the t component is what keeps it moving forward on x. The 1 minus cosine t, that's what has it going up and down and up and down and up and down and up and down, you know, like that. The t minus sine t, minus sine t is moving more slowly here because sine is positive and it's subtracting away. But here it's adding 2, so it increases its motion in the positive direction, but then decreases it here, increases it again, decreases, increasing, decreasing. That is the rate at which it's going in the positive x direction, but it's always positive. The y is going up and down and up and down, so it's sometimes going positive, sometimes going in a negative direction. It never reaches zero, negative numbers, but it stops at zero and starts over again. Okay, now those aren't sine curves or half sine curves or anything else. They're the curves we talked about, these curves right here, parametric curves. Now, if you had, the first was a circle of radius 1, okay? That was the first curve we saw. And that's the parametric equations for circles of radius 1. If you had a circle of radius r, like a bicycle wheel or any kind of wheel that's not got a radius of 1, then this is what those equations become. Okay? And again, pretty reasonable. X is equal to RT minus R sine t, and y is equal to R minus R cosine t. So whatever your radius was, that's your starting point, or the center of the circle, basically, from here. And that's the starting point, and it goes forward after that. Now, I don't think you'll ever get this to be greater than that. This always leads that. Sometimes it leads it more and sometimes it leads it less, but it always is leading. On this one, it always has the croquet fashion, or that pattern going up and down, up and down, up and down. Okay, so that's the that. I'm trying to see. Oh, this is the figure that they use to try to reconcile maybe a little bit your I think I've got it okay there. Okay. This is going back to the unit circle one. Not really a unit circle, but a wheel with, or a circle with a radius of 1 that's rolling along here. Okay. As it moves from 0 to, say, t here, what it's doing is showing that this is that length t that the ball has followed this path, but the position that this point has taken in getting from here to there, it's actually moved from here to here, but it's I guess it's back to what I was saying before. This is the t part. This is also your angle t. Actually, what they're showing here is the movement of the center of the circle. The center of the circle is moving the t. Okay, the particle relative to the center of the circle is actually backing up some, but the center is moving that way faster than the particle is backing up. So that's why it's going pretty slowly up here to begin with, and once it passes overhead, which occurs right here, then when the t is moving forward, it's really picking up effort, as it goes there. So here is the t, and this is the angle t. So from the point, now, this didn't start here. It started here at this position. What this is showing, I wish I hadn't done a blue dot there because that makes it look like part of this pattern. It's not. If I had to do it something, I would have chosen a different color. But this is directly underneath here, meaning this is a right angle. That makes this a T, and that's an increasing T here. In the time it's taken the center to go from 0 to T, this is turned, because this is a unit angle, T, the curve here is T, okay? And that angle's T, and actually how far it has gone in that time the center went this far, the ball here, the blue dot here, actually started here and almost seems like it's moved backwards. You're subtracting a positive number from it, but it's not nearly as large as the projection forward of the center. So that's why it's following this path upward. And it continues rolling around there. When it gets at the top, which is here, and continues rolling, now the angle is, the center is still moving at the same rate, but now the angle is moving in the same direction and increasing this. So here it's a slow increase here. That's why it's almost vertical here. But somewhere up here, then it'll pick up. I mean, just really is moving rapidly this way. Now, let's look at the y value as well. That's y is equal to 1 minus cosine t. It starts off t equals 0, it's at 0, okay? And then as t increases, the cosine is getting smaller, so the movement upward is faster than the movement down. So, movement across, to the right. And here is the line y is equal to 1 minus cosine t. It's starting up here and then moving down because 1 minus cosine t is a decreasing function, but the center is moving here, so your cosine and here's another thing, it just dawned on me was the situation here. This t starts off being 1, t is equal to 0. And then as t is increasing, cosine t is decreasing. So you're subtracting a smaller number from 1, so that's why it's moving upward. Okay? So cosine t, again, with this angle being t, unit circle again, this angle being t, the cosine of t is the y value of that. Okay? So your 1 minus that is getting less and less. It was a full 1 here, 1 minus that, 1 minus this, and it keeps decreasing. The cosine is decreasing, but 1 minus cosine is increasing until it reaches here, and there it would be 1 because cosine of t is 0. The cosine of pi halves is 0, but then it keeps on going up and when it reaches pi, it's 1 minus a minus 1. So it increases for that first half of the term till it reaches pi, and then it starts decreasing again. It never goes below that. So that's the diagram. The t is in this direction. Sine t, because it's a minus, is back here from the t. The 1 is where you're starting from here, minus cosine t, which starts at 0 here, but it's decreasing as you go up until t gets to be pi halves, and then that's exactly 1, because cosine of pi halves is 0, and then it flips over and starts moving upwards, so it gets up to 2 somewhere down the road. So that's generally the pattern, okay? Now, do they do anything else with that? No, I thought we were going to give an example, but they don't. But here's some of the things that you do get out of this. I thought they were going to mention it now, but I don't see it here. There are all sorts of curves that relate to that cycloid. Like I said, the power lines do. One of the big deals about that, this is a strange way to say it, but it's indeed true. Let's flip this over and have your cycloid on the underneath side. I hope I'm remembering this right. The speed at which, say, a drop of water would move down that curve, okay, get to the bottom, you would think it would fall more rapidly here because it's a steeper curve here, but if my memory's right, it always takes the same time for it to travel any distance. Of course, a drop of water wouldn't move uphill, but it makes for an interesting problem like that. You know, if you read up on that, you'll see that there's a vacuotome or something like that follows that pattern as well. And it does show up in nature in a variety of ways. I thought the book was going to give more examples, but it doesn't. Okay, let's move on to really what's, I think, is far more important. I just spent way too much time on that one because I thought they were going to do more problems on it or examples on it. So I wanted you to understand it better, but it must have been back in another chapter somewhere or in another text. Here's theorem 2, slope of a tangent line. Let's say that C of t is this curve, x of t, y of t, whatever that happens to be, where x of t and y of t are both differentiable functions. Okay, they're each differentiable. Okay, I hate to do this again, but I'm going to do it again. That curve there, and it may not show it so well here, so let's go back to this one. Okay? I think you could buy from me that this curve looks like it would be differentiable everywhere except here, here, and here. Because if you think about it, that is definitely a cusp there. And even though it's a continuous function, it's not differentiable at the multiples of 2 pi, because here the slope seems to be extremely positive when you start decreasing. Then it's decreasing, decreasing, decreasing until it reaches there, and then it's suddenly positive again. Actually, there, the first derivative is of the curve here is not defined at 2 pi's. But that's not what they said. They said that the x and y are differentiable everywhere. Let me go back before I change this, okay? And if you remember these functions here, yeah, well, I'll go to this one. This is differentiable everywhere. This is t minus cosine t. I'm sorry, 1 minus cosine t. And this is positive sine t. Differentiable everywhere. The parametric equations are differentiable everywhere. whereas the resulting function is not differentiable everywhere. And there's a reason for that, because your derivative, and here's the slope of a tangent line, and this will, I think, come out here. Goodness, my eyes are dry. C of t is x of t, y of t, where x of t and y of t are both differentiable functions everywhere, or at least on the interval in question. Assume that x prime of t, differentiable, is also continuous, that the first derivative is also continuous, and that x prime of t is never equal to 0. Okay? Then dy dx, which is the slope of the overall function, when you plotted the parametric curve, this would be, and you plotted x, y of the parametric curve, like we were doing, then your dy dx would be dy dt over dx dt. This is why it says x of t, x prime is never equal to 0. As long as this is not 0, then this result comes, y prime over x prime. Now, that was the problem back here. At these points here, your dx dt is infinite. Okay? If you think about it, here's the function, dx dt. This would be 1 minus cosine t, right? And we know that 1 minus cosine t is already this. It varies up and down like this. So every time it hits 0 again, the first derivative of x of t, which is y of t, that would be 0. And then those places your dy dx would not be defined. Okay?
So if your x prime is equal to 0, then you can use that theorem.
Okay, say that one more time.
If your x prime is equal to 0, then you can use that theorem.
Okay, x prime equals 0 what?
That theorem's not valid for an equation.
Okay. Yeah, because your dy dx can't be an infinite thing. What happens is x prime of t is 0, then this is not defined. Okay, so yeah. But everywhere else it is defined. Okay, up to where it's 0, but not where it's 0. Okay. Then this is be what your dy dx is y prime over x prime. Okay. That's with respect to time, or t, whatever your t is. So let's do example 9. Now, example 9, and this is what was driving me nuts before, they didn't put the figure for example 9 what I thought they would. They got it over here, okay? Or maybe they did, okay. Let's look at it for a moment here. Here is the function. C of t is t squared plus 1, comma, t cubed minus 4t. Okay? Now, and this is giving away part of the problem here, so I won't go into great detail about it. But we did this one already. We graphed this function. Okay? Now, at t equals 0, you're at 1, 0. It's right there. Okay? At t equal 1, you're at 1, negative 3. That's down here. Okay, or somewhere down there. 2, negative 3. Yeah, 2, negative 3. T equal 1. That'd be 2, negative 3. At t equal 2, you'd be at 5, 0. And at t equal 3, I think someone did it earlier, and that would give you 10. And show here something around 15, is that right? T equals 3, that'd be 9 minus, yeah, down here, I'm sorry. T equals 3 would be 9, 9 negative. I'm not really able to do this. Equals, oh, that'd be 27 minus, yeah. So is it minus 12 or minus 15? Why is my brain not working? Yeah, that would be minus 12. That would be 27 minus 12 would be 15. Yeah, minus 15. So sure enough, that's where it is. And then it goes up there, and when t is negative 2, this again would be 5 and 0. But when t is negative 3, this would be 10 still, and this would then be positive 15. Yeah. So that's the same curve we had before. Now, that's just showing the curve. All right. And it asks for 3 things. Okay, with this curve. Find an equation of the tangent line at t is equal to 3. Okay, we want an equation of the tangent line there. So how can we get the equation of a tangent line? What are we going to need? Any ideas? Equation of a tangent line. Say again? Okay. How about an equation of a line in period? There can be several forms. Y is equal to mx plus b if we had slope and y-intercepts, or y minus y1 is equal to m times x minus x1. That would be a point slope formula. Okay. Now, I think for this problem, in fact, I know for this problem, there's not going to be a place where x is equal to 0. We've already shown that. X is never equal to 0. So we're not going to be able to do this equation. So that's my favorite. But I think we can do this one. And we said equation of the tangent line at t is equal to 3. Okay. So we need 2 things there. We need the point at t is equal to 3, and that's not too hard to get. Okay? Here's c of t, so we want to do c of 3. And we've already done it. What was that? 10, comma, say again? Was that 15 or negative 15? It's 15. Now wait a minute. Yeah. Okay. Yeah, because it's 27 minus 12. Yeah, 15. So there's our point. This is our x1. This is our y1. So we have a point. Got that. What we also need is m at that point. We'll call that m1. Okay? And what do we say that was? That's the slope is your derivative of the tangent at t equal 3. So we need to figure out what the derivative of the tangent at t is equal to 3. What did the last, was it theorem or definition? Yeah, theorem tell us. What's the slope of the tangent line? M of the tangent line at t is equal to 3 would be what? Say again? No. The slope of the tangent line. Remember what the previous one? Let's go back there. Here it is. dy dx, and this will be at t equal 3, would be y prime at t equal 3 over x prime at t equal 3. So what we've got to do to get that is get what x prime is. That's as a function of t. So let me do this. So, since you got so many variables, dx dt. Rather than x prime, I'm going to call it dx dt. Okay? Easy to get, right? What would it be? 2t, okay? And dy dt is equal to what? 3t squared minus 4, right? Understand you right? Right? Okay. Now, the slope then would be dy dt over dx dt. But we want those both evaluated at t equal 3. Okay, so let's go on and evaluate them at t equal 3. dx dt at t equal 3 would be 6. dy dt at t equal 3 would be 23, you said? Okay, I think that's right. Okay, 3 times 9, 27 minus 4 is 3. So the slope here would be 23, 6, which I can't reduce. Okay, it's just 23, 6. So let's plug that into our formula here. Y minus, your y1 is t equal 3, that was 15, right? Minus, or is equal to the slope 23, 6 times x minus x1, which was 10. Okay, now we can probably clean that up a little bit. In fact, I think I'll do it this way. I'll probably regret this, but I think I'll do it this way. Multiply both sides by 6, right? And this gives us 6y minus 90. 6 times 15, yeah, I'm pretty sure that's 90, right? Is equal to 23x minus 230, right? Okay. Before I go any further, let me just see what form they're going to give it to us. They left it. Yeah, they left it in this form right here, okay? That is an equation of the tangent line. They didn't solve for y. They didn't do anything else. They left it in exactly that form, which is fine. That's an equation of the tangent line. Now, do you see why I sort of tend not to do event Weber sign and things like this? If they had asked for that problem, that's the last form I would have thought they would have wanted it in. But if they ask for that as a thing on one of those programs, they're only looking for one form. Which form are they looking for? Unless they say slope-intercept form or standard form or something else, you don't know. And I never would have guessed they would have left it like that, but they did. Okay. So we've done the A part. That is that. I was going to do this. I was going to say 23x minus 6y is equal to 140. Okay? That would have been another equation for the line, but they didn't have it in that form. It looks a little better than that one, but still, that one says point slope form, fine. Leave it alone. The B part says, the points where the tangent is horizontal. Now, what's true about a horizontal tangent? Okay. Where, that's a weird way to say it. The points where the tangent is horizontal. Okay. What's true about a horizontal line? It's every horizontal line. No, y wouldn't it be equal to 0? Y prime would be equal to 0. Okay? The slope is 0. Now, if that's your slope, that's going to be 0 only if that numerator is 0. And that numerator is dy dt, because you don't ever want the denominator being 0. That's going to be your vertical line. That's going to be right there. So you don't want that to happen. But it's where the slope is 0, that should dy dt is equal to 0. and your dy dt, I know we had it right there, set that equal to 0. Okay? So set that equal to 0. And what do you get for t? Because it says find the points where the tangent is horizontal. That would be where dy dt is equal to 0. Let's find out what values t that would be, and then plug those values into your the curve. Okay? So where is that equal to 0? What would you do? Add 4 to both sides. That would be 3t squared is equal to 4. And then divide both sides by 3. Okay, and that gives you t squared is equal to 4/3. Now what would you do next? Take a square root of both of those, and you get t is equal to plus or minus 2 over root 3. Now I'm perfectly happy in that form. Okay, you could say 2 root 3 over 3 if you don't like having radicals in the denominator. I'm okay with it now. Okay, you can plug it in your calculator without rationalizing the denominator. It doesn't take the calculator that much longer to calculate that. It just doesn't. But those are the two times when your slope is horizontal. All right, now if you plug those in to your formula here, your curve at, let's do plus 2 over root 3, would be, well, if t is equal to 2 over root 3, what is t squared? 4 over 3, exactly. Plus 1, okay, and your y value would be 2 over root 3 cubed minus 4 times 2 over root 3. Now, that's a little messy, but 4/3 plus 1, that would be 7/3, right? Right? Okay. Is your x value. Your y value here is, it would be 8 over 3 root 3, because the square root of 3 cubed, square root of 3 squared is 3, and then times another, okay, that's it, minus 8 over, that can't be right. Yeah, well, wait. Okay, what have I done wrong here? Two over root 3 cubed. Oh yeah, 8 over root 3. I did it right. Okay. I thought it was the same. Okay. Now, if you look at this, you'd have to multiply this by 3 and that by 3 to have same denominators. So that would give you, the x value is still 7/3. The y value is negative 16 over 3 root 3. Okay. So that's when t is equal to positive 2 over root 3. So that would be this point right down here. The x value is 7/3, which would be 2 1/3. That looks about right. The y value down here at, you can work that out with the calculator and see what it is. Looks like it's something maybe close to 4, maybe a little bit less than 4. I don't know. Plug that in your calculator and see what you get. 16 divided by 3 root 3. Anyone got a calculator handy? 16 divided by 3 root 3. Root 3. Yeah. Have you got it?
Yeah.
What would it be? Number, numerical. Yeah, decimal number. I'm guessing it's a little bit more or less than -4. I just don't know if it's -3 point something or -4 point something.
-3.079.
Oh, really? Okay. Closer to -3 then. Yeah, I guess that's right. So, something like -3. And this, we already knew would be that. Well, if we plug in the minus there, then C of -2 over root 3. Guess what? Your x value is exactly the same. Because -2 squared is still 4/3 plus 1. So that's still our 7/3. And that's why these are right on top of each other. And then when you put the minus in here, though, here we go. We'll do it here. This will be a minus 4/3 root 3. No, 8/3 root 3. Yeah, minus 8/3 root 3. And then you have plus, because minus a minus is plus, 8/root 3. And now everything's just turned around, as the sign's just different. So this will be 7/3 16/3 root 3. No, not, huh? Say again? Now this is a positive. When the t is negative, this one is bigger than that. And that's your plus, that's your minus. So yeah, it's a positive value. So that's why it's right above it. Okay? So those are the two places that you have horizontal tangents. And the only two places, by the way. Okay? You do have one vertical tangent, and that would be when your x was equal to 0. X prime is equal to 0. I'm trying to find my x prime now. That's it right there. That's it. T equals 0. T equals 0. You're at 1, 0. So yeah, that's the place you have a vertical slope tangent line. Are we already out of time? That's so sad. Okay. I think we just did both of those. We'll start next time on what they call Bezier curves. I hope that's how you pronounce it. Parametric curves, widely used in the field of computer graphics, and we'll pick up there next time. Let me give you a few homework exercises here. We almost finished 11.1. So you can do any of the odds 1 through 5. Goodness, I think I just, okay. Any of the odds 7 through 13, either 15 or 17. Either 19 or 21. Any of the odds 23 through, 37. Either 39 or 41. Let's say any of the odds 43 through 47. Any of the odds 49 to 53. And any of the odds 55 to 50, either 55 or 57. And 59, I think you can do. I think you can do 61 or 63. perhaps 65, and stop there. Let 65 be your last one. Go as many or a few as you can of those, and we'll pick up from there with the Bezier curves. Sorry we didn't get as much done today as I had hoped. We spent too much time on that cycloid. Okay, good deal. We'll pick up and go from there.